Hello, class. I want to maybe do a computation inside a permutation group. So suppose I have like 1, 2, so I should tell you where I am. I'm in S6, and I have 1, 2, 4, 3, 6. X is equal to 2, 5, 1. No. Let's make it 3, 6. No, 3, 4. Okay. So that's a computation that I clearly just made up on the spot, and I want to solve it. So how do you solve something like this? Well, this is something of the form ax equals b, and the thing I want to do is I want to multiply by a inverse. And what do we have to do? Well, we have to talk about how to take an inverse of something here. And this is actually really easy to do in cycle notation. This is another strength of cycle notation. So what is the inverse of a single cycle? So let's think about it. The inverse of a single cycle. So what is this saying? 1 goes to 2, 2 goes to 4, 4 goes to 1. So what would be the opposite of that? Well, everything goes to, instead of the thing to the right, the thing to the left. So 1 goes to 4, 4 goes to 2, and 2 goes to 1. I could even do this. If I don't care about how it's written, I can just reverse all the elements. So for example, if I have 1, 7, 9, 2, 3, 5, 6, and this is an S9 now, and I want to know the inverse of this, this is equal to 6, 5, 3, 2, 9, 7, 1. And if you want to write the 1 in the front, well, this happens to be equal to 1, 6, 5, 3, 2, 9, 7, because the 1 goes to 6, and all the others go the way that you can see that they go from that cycle. So the inverse of any single cycle, you can either start in the beginning and then start moving left in order to find it out, or you could just actually just reverse all the numbers very fast. So if I want to know the inverse of, say, 1, 2, 4, 3, 6, the inverse of that entire thing, well, what do I know? Well, the elements in these two places don't interact at all, so I just find the inverses of them both. Now, you might have an objection, but we'll get to that. 4, 2, 1, 6, 3, which I could write as 1, 4, 2, 3, 6 if I want, and that's the inverse, and that's my answer. Okay, let's actually do this computation, and then I'll get to the objection. Looking at this right now, I'm going to multiply both sides by this. So that's going to just give me an x on the left, but on the right, I get this. Keep in mind I multiplied both sides on the left, right? So I multiplied this on the left, so that cancels, because I know that's the inverse. And then I multiply this on the left, because I have to multiply on the same side. So what do I get here? Well, x is equal to, let's see, where does 1 go? 1 goes to 1, to 1, to 1, to 4. 4 goes to 3, which goes to 6. 6 goes to 3. 3 goes to 4, which goes to 2. 2 goes to 5. And 5 goes to 2, which goes to 1. And I close it. Now you might say, hey, did you have to do that last 5 goes to 1? Isn't it obvious that 5 is going to go to 1? Yes, it's obvious, but you should check your work. It's a good idea to always check before you're closing the parenthesis and not just assume that things are going to work out. Okay, so I said I had an objection, and that's true. Because if you have two things and you do them in order and you undo them, well, you have something called the socks-shoes principle. And that means, hey, if you put on your socks and then put on your shoes, you want to undo the process. You don't take off your socks and then take off your shoes. You undo each of the processes in the opposite order. So basically that principle says that AB inverse is B inverse A inverse. And you do have to keep this in mind because things don't necessarily compute. So did I do this wrong? I just I just applied the inverse to both of them in the same order, and the reason I did that is because it doesn't matter. You see, if you have disjoint cycles like 3, 6, and 1, 2, 4, and they don't share any elements in common, then they're going to be the same. Doesn't matter how I write them, because this is telling me where 1 and 2 and 4 go, this is telling me where 3 and 6 go, and there's no interaction between the elements here and the elements here. So to do this out, red, orange, yellow, purple. If I change 3 and 6, put that there, and then have 1 goes to 2, goes to 4, hold on, 1 goes to 2, 2 goes to 4, and 4 goes to 1, and the 5 just drops down. Notice that it didn't matter that I changed the 3 and the 6 first. I could have left the 3 and the 6 and just changed that last, because none of the motions of the other blocks affects that 3 and the 6. So, because of that, when you have disjoint cycles, which is just an element in cycle notation, right? Every element in cycle notation is a collection of disjoint cycles. When you have disjoint cycles, you could just take the inverse of each of the elements in any order you like. Each of the individual cycles in any order you like. That's what I mean. So for example, in S8, if I have 1, 2, 3, 7, 4, 5, and I want to take the inverse of all of that, it doesn't matter which one I write first, because I can write any of these three things in any order. But notice that if I reverse this, I get 2, 1, which is the same as 1, 2. So here, this element is its own inverse. Okay. That's always going to happen when your element is composed of a collection of 2 cycles. Disjoint 2 cycles, of course. Because if you switch the order of 2 elements, it doesn't matter how you write them. And that is true. So that's a lot of different things that we've been doing. So we now know how to do solve for computations in S8, maybe, or in SN in general. Maybe we'll do one more quick one. Let's say we have 1, 2, 5, 7, 3, 4, x equals 1, 3, 7, 6. Okay, and I want to solve this. Well, I want to take the inverse of this. So if I call this A, I know that A inverse is going to be 7, 5, 2, 1. I could write 4, 3 here, but we already know that's going to be 3, 4. And I could even write this as 1 goes to 7, goes to 5, goes to 2, to 3, 4. Okay, well, applying A inverse on the left to both sides means I get this, 1, 7, 5, 2, 3, 4, times 1, 3, 7, 6. And let's do this multiplication. 1 goes to 3, which goes to 4. 4 goes to 3. 3 goes to 7, which goes to 5. 5 goes to 2. 2 goes to 1. And that's it. What about 6? Let's see where 6 goes. 6, because I haven't taken care of 6. It's not it. I have to finish this. 6 goes to 1, which goes to 7. 7 goes to 6, which stays at 6. So now that's it. I've accounted for everything. The last thing you might want to say is, okay, where were we? I don't know if I even said. If we're in S7, we know where all the elements are. If we were in, say, S10, we might want to make sure that 9 and 10 don't go anywhere, but obviously they wouldn't, because no 9 nor 10. 10 does not appear as well. So neither of them appear. Neither 9 nor 10. So that's those are some examples involving solving equations in the symmetric group, and some other details which are included here in this video for the first time. And it probably is a good idea to practice solving some equations of the form ax equals b now.